At least Mr. Fournier will curse on live TV like Donald Trump.
We have all of
So
our words.
yeah, this is what we call this type of motion. It's a very interesting motion, which is why it's like the whole topic of this unit is called simple harmonic motion. Simple harmonic motion. So that's what this is that we're talking. So a spring mass system, an ideal spring mass system, and an ideal pendulum obey motion that we call simple harmonic motion. How about that? Simple harmonic motion. Okay. Yes. So now, if an object is oscillating, it doesn't have to obey simple harmonic motion. It doesn't need to. But these things with an ideal pendulum, ideal spring, they do. So all right. So I got basically this diagram. What it's showing is here's the equilibrium position for a spring mass system, and then I can displace that spring, let it go, and it'll just go whoop, 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 right? That, forth. Yeah, I saw a lot of people, like dancing to their mass, yeah. So even though I made the dashes here just to show it's a ground, it is a frictionless surface, and I'm also not doing it. I know you guys did it vertically. It turns out that even if if it's vertically, you got basically the spring force and the weight pulling down, but it turns out it still will obey simple harmonic motion even with that thing there. But yeah, so with this, I mean, what's the only force to be acting on the mass if it was oscillating back and forth? The spring force, yeah. We got an equation for that.
Yes.
Right? It's
x kx.
Yeah, kx, right? So or k delta x, we could say. Right? So it's k delta x, it's the spring constant multiplied by its displacement from equilibrium. So if I said my original position is 0, then I don't need the delta x, I could just say x. So whatever the position is with respect to that equilibrium position, which is my origin, yeah. And now, again, I think I said this when I first introduced this, that I tend not to like to write this next part, because it just kind of confuses students, but it's definitely going to be useful for us when we talk about this. Is that you got that negative in there as well. You got that negative in there as well. And what the negative is suggesting is that whatever your displacement direction is, the force points the opposite direction. So if my displacement points to the right, which way does the force point? To the left. And then if my displacement points to the left, the force points to the right. Yeah. There we go. And that's what that is basically showcasing. But what happens is when people plug it into F net equals ma, they take into account the negative when they're using F net equals ma, then they throw in the negative, and that's where the confusion shows up. But anybody remember what law this is called? Hooke's law. The guy who had a few. I found out. I just found out recently. I guess like Newton, like every like scientist, they would have like feuds with each other, and like
Do you have one?
they would publish like insults at one another and things.
Do you publish insults about why?
What's that?
You and Brian fight a lot with each other.
Yes, yes.
No, guys,
To
we need
reflect
Mr.
science.
Four games.
Yes, and basically, an object will undergo simple harmonic motion if its motion obeys Hooke's law. We'll get a little more detailed in this class. Even if you took AP 1, you haven't gotten this detailed yet. So we'll get a little more detailed because we're going to be using some differential equations later on in the week, next week. About how you can use that. So if it obeys Hooke's law, you can go, great, now I can use this differential equation and find out what the period is really quickly. Okay, yeah, so, but if it obeys Hooke's law, it undergoes simple harmonic motion. Springs definitely obey Hooke's law. I mean, that was like where we kind of got Hooke's law from. But even something, if you got like a rubber band, so elastic, so if you got somebody going up and down on a bungee, right, after they, just before they break their head or whatever, you know, but, or even a pendulum obeys Hooke's law, in which the force is often called the restoring force. The restoring force. So sometimes they might say like, oh, here's an object that's oscillating, calculate the restoring force. What they mean is, you know, calculate the spring force. Use Hooke's law to find out what that, and it's called restoring force because if you think about it, as it's displaced, it keeps wanting to go back to its equilibrium. So as it goes this way, it's going, oh no, I want to go back, but it always overshoots. It goes, oh dang it, and then it goes, oh no, I'm not. This is, yeah, yes.
So, wait, but how does a pendulum really like? Is it like the string itself with the mass, or is it the motion of going left and right?
We'll get to it. We'll get to that. We'll get to that. That's what we're gonna do Tuesday, and that's why you're gonna be able to calculate. I'm sorry. Say that one more time though. What you're asking?
I'm just like, because you said it applies to like pendulums. So is it like the motion itself of moving left and right, or like the string and like?
Oh, the motion of the mass.
Okay.
Yeah, the motion of the mass. So it's oscillating back and forth and back and forth and back and forth, and that undergoes simple harmonic motion. You'll see in the way we model it of why the motion is similar.
Okay.
But unfortunately, that's not till Tuesday. Yeah.
So, would it be different because the spring's moving, like how Tony said, it's moving only vertically, but that has some tension force on it.
Exactly.
Oh, I see. Okay.
Because he's saying it moves left and right, like this one moves up and down, but also has, like the tension force holding it. That's,
Okay.
That's like opposite from the direction.
So when hold that thought right now.
Okay.
When we derive it in class, see if that makes it make sense. So that'll be Tuesday.
Okay.
But hold on to it because I don't want yeah. But it'll be answered later on. Okay.
Thank you.
Okay. So
The dots are like the.
you'll see in a moment. Oh, and then also. This would be like the maximum. If I did this, held it here and let it go, it would go back and forth and back and forth, and that's the we call that the maximum displacement from equilibrium because it's the maximum displacement from equilibrium. But we have a simpler term for it. What do we call that maximum displacement from equilibrium?
Wait,
Repeat? Press?
Delta X.
Delta X max.
Delta X would be the displacement, but you can this would
Delta
also
X
be the
max.
displacement here.
Absolute value of delta X max.
That's
That's a lot of words.
That's right. We call it the amplitude.
Oh, yeah, we're in harmonic. Right.
Shoot.
Whoops. We'll just call it a ridiculously harder name.
I will talk about crests and troughs when we get to waves.
Oh, shoot.
So amplitude, yeah, and then obviously to the right of the equilibrium position, we call that the positive amplitude, and then this would be the negative amplitude. So you'll see that with like graphs and things like that we start making. But what I want you guys to do right now is to draw for me vectors. Draw for me these three positions of where the spring is. Draw for me what direction the force vector would point. Where would the force vector point from here? Where would the force vector point here? Where would the force vector point there? Well, what? Either.
Hey, I got you. The velocity
Yeah, because the force point
Oh,
is
I don't know.
displacement, so this one is right there.
Yeah, but like if you're at the center, does your
This
force
is
point
like
down?
the arrows.
Because that's like
Right where it changes direction.
Sure, relative magnitude. So if you draw the force one vector and it's supposed to be the same the other way, yeah,
Like
relative.
some arrows longer than the other.
Yeah, whatever.
That's
Wait, do we also have to,
Just the net force.
for only the extra of the y, the way it's net?
There is no y. Does it go up and down?
Oh, there's no force when it's at the center, or also it's
It doesn't have an acceleration.
I just do it the same way I do it today. But that's not equal than A.
It's the same thing, right?
Dude, listen. F net.
Wait, do we say
Yeah, no. There's no acceleration in the y direction, so.
That's like
Was that-
a roll in GMS, we need to draw.
Okay, we will.
No,
Wait,
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 wait, cancel
Well,
out, 'cause
in a
it's
moment.
just a F
There's
net.
one by one.
What are we
Isn't the energy's like nothing?
F net.
No,
That's
talk
like
about
At the end it stops for a tiny bit, and at the other end it stops.
All right, so
I zoned out.
here, what direction is the force point?
To the right.
Right, yeah. What about over here? Which way is the force point? That's basically what we just talked about, right? About base Hooke's law.
Yeah.
So, all right. What about and what about in the center? Which way is the force point?
There's no force.
And there is no force. Yeah. Yeah. Only upon the force. That's right. And what would happen to the force though as it gets closer to the equilibrium position?
It gets smaller, smaller,
smaller.
It gets weaker and weaker and weaker. Yeah.
The magnitude.
According to this one, it won't be like, it won't disappear. So we have to do that.
So again, it gets weaker and weaker and weaker. Oh, you're already getting there, yeah. I mean, basically that's what we're gonna get to. Okay, now we're gonna skip velocity for a moment, do acceleration. Draw for me the acceleration vector. Again, at those three different positions.
I was skipping velocity. Isn't it the same thing as acceleration?
Is it?
Oh, that's how you do it.
Yeah.
Yeah. It's like, it depends, so.
Hey, think about it. They're like, it's like moving and then it stops, right? So what do you?
Wait,
I didn't have.
Mr. Forney, if it oscillates for a while, doesn't it lose?
It does. So again, we're assuming an ideal spring mass system and an ideal pendulum. So no damping, no
March
air
and
resistance.
April.
No, I'm saying, should we
3.5.
stop it? Cause it's gonna, the spring's gonna be doing.
Oh, I see what you're saying.
Should we just?
With the mass I have, it shouldn't.
Oh, but still, we don't wanna ruin the.
I appreciate that. Thank you. Thank you.
We don't wanna sell candles.
That's why you're the camera guy.
Can we hold it so? Hey, Mr. Forney,
Huh.
are you gonna be at our graduation?
Yes.
Wait, now that
waiting here.
if we're graduated students, can we go to that?
Huh?
Can we go to that? If we just graduate?
My graduation?
You have a huge, like 100 student fan base just doing
So, all right, we got precious little time. What would the acceleration one look like?
Same as the
Exactly as the force, yeah, exactly. Now it might be scaled up differently, but why? F that equals ma, yo. So that's the net force. So the net force is the same, always the same direction as the acceleration, because mass is never negative. All right, now try the velocity one.
Oh, it would be great. Oh. It should be like long.
I would say here is spring and kinetic.
Yeah, it's like.
All the way. Because all the kinetic and spring and zero.
Can you draw an arrow that starts away from the dot?
What's that?
Yes, you can.
No. Dude. Our cap.
All right.
Always almost due too.
So have your velocity prediction. The bell's going to ring soon. Once again, you don't have to do homework 15, which there's nothing to do anyway because I didn't write anything. And then make sure you got your graphs completed and ready to present on Tuesday.
Oh, it's 3D weekend.